This video is about tests of association, and we're going to look specifically at correlation and multiple regression. Tests of association involve testing the correspondence between two continuous or ordinal categorical variables. They can be visualized with scatter plots. So here on the top left, we see as x increases, y decreases. This is a negative correlation. In the top right, we see a positive correlation, whereas x increases, y increases. In the bottom left, we see no correlation. There doesn't seem to be any correspondence between x and y. The points are random. And then in the bottom right, we see a nonlinear correlation, where as x increases, y first increases, then as x continues to increase, y then decreases. Multiple regression is an extension of correlation, where we test for the correlation between multiple independent variables and one dependent variable simultaneously. And we'll talk a little bit more about what that means. The data we're going to be looking at to demonstrate how these tests can be done is from a study conducted here at Fordham, where we examined people's trust in statistical algorithms for making predictions about different types of events. Trust was measured from 0 to 100. And an example of a statistical algorithm for making predictions might be something like 538.com's election forecast model. So this is a very popular model for predicting the results of different elections. And right here you see the current forecast for the upcoming presidential election. And just take a second to think about what you think this forecast is like. Do you think this is a good forecast or a bad forecast? And do you generally think statistical models like this are well suited to make forecasts about things like elections? That's the type of thing we were studying. So first we're going to talk about simple correlations, which check for the association between two variables that have meaningful ordering. Correlation ranges from -1 to 1, with -1 being a perfect negative correlation and 1 being a perfect positive correlation. If both variables are continuous, we would use the Pearson correlation. So an example might be age and trust in statistical algorithms. So do we think that as people get older, their trust in statistical algorithm changes? Another example might be education and trust in statistical algorithms. And in this case, education is a categorical variable that has meaningful ordering. It's not continuous, and therefore we would use the Spearman correlation. So let's switch over to the SPSS window and take a look at how to do correlations. So here's the SPSS data view. I already have my data all loaded up. So we can just go ahead and analyze it. And to do that, we click the Analyze menu. We go to the Correlate section, and we choose Bivariate. And this is what it's going to look like when you first open it up. And you want to put the two variables that you want to correlate here from the left side. The left side lists all the variables in your data. And you want to choose the variables that you're correlating by putting them here on the right. So here we want to choose age. And our dependent variable is RESP, which is the response to the question about trust in statistical algorithms. We also want to click the Options menu and select Means and Standard Deviations. This just will ask SPSS to also give us some descriptive statistics, so we don't have to do that separately. We can do it all at once. And then we run it. And here are our correlations. And here at the top, you see, because we asked for means and standard deviations, we get these descriptive statistics for both of our variables. And then here at the bottom, we get our correlation table. And I'm going to go to an editor where I can draw just to take a slightly closer look at this. So here we go. So here's what we have with this correlation table. This is a 2x2 table, which means we have both variables, age and RESP, on the top and along the side. So then for each variable, we have a comparison between them. So here in the top left, we're comparing age to age. Obviously, age and age are perfectly correlated, so it's 1. And then we have the same thing with RESP down in the bottom. It's perfectly correlated with itself, so we can pretty much ignore those parts of the table. What we're interested in are these off parts where we're comparing RESP with age. And again, it's the same thing down here. We have RESP and age. These are identical to each other, so we can just look at one of them. And here we see the correlation is -0.133. The two-tailed significance is 0.036, and the sample size was 250. So what this tells us is that the correlation between age and trust in algorithms is statistically significant, and it's negative. So as people get older, they tend to have less trust in statistical algorithms. So these are captured in screenshots for you on the slides for reference. And that's it for simple correlation, and now we can talk about multiple regression. Multiple regression tests partial correlations. What that means is it's simultaneously testing the association between one dependent variable and multiple independent variables. And when we say partial, what we mean is that we're testing the relationship between each independent variable and the dependent variable after controlling for each other independent variable. And this tells us two things of interest: the amount of variability in the dependent variable explained by all of the independent variables at once. And it also tells us the amount of increase we would expect in the dependent variable for every 1 unit increase in an independent variable while holding all other independent variables constant. So an example might be we want to know the relationship between age and trust in algorithms, but we want to control for the fact that people also have different levels of education. So to run a multiple regression in SPSS, let's hop back over to the SPSS data window. We can click Analyze. We go to Regression, and we select Linear. So we're going to want to put our dependent variable in the dependent section, and we are going to put our independent variables in the independent section. So in this case, we want age, and we want education. And then under statistics, we have estimates and model fit selected. We want that. And then we also want descriptives. Again, this just prints out our descriptive statistics, so we don't have to do it multiple times. And then we run it, and we get several tables here. So this first table, because we asked for it, we get these descriptive statistics for each variable, just nice to have so we can reference. Then the second table is a full correlation table. This isn't actually our regression results, but I'll show you a little bit about what this table is by going to an editor. So here we have this table. So this is showing a 3x3 table comparing each variable to each other variable. And so this top section is the actual correlation. So here you see along the diagonal, we have all ones because this is each variable being correlated with itself. If you look here, when we correlate age and RESP, we get the same negative 0.133 that we got before. And so these are just simple correlations between all of our variables. And then the second section is our significance tests of these simple correlations. These are one-tailed tests, which is a little bit tricky. I'm not sure why SPSS does it that way. To get the two-tailed version, you just multiply them by 2. So you see this 0.18, to get it to be the 0.36 we had in our first analysis, we just multiply it by 2. But this isn't really our main interest in a regression analysis. So our main interest in a regression analysis is down here at the bottom. We can ignore this variables enter and remove table. That doesn't tell us much. So these last three tables are our real results of interest. So I'm going to go back over to an editor so I can circle things. So this model summary table gives us two things that we're interested in, really one thing. It's R square and adjusted R square. These are effect sizes of the full model. So this is the amount of variability in the dependent variable explained by all of the independent variables at once. And that's what R square is. So we would say that 2% of the variability in trust in algorithms is explained by education and by age. Adjusted R square is just a slightly different version of R square that penalizes it for each extra variable you add because R square tends to be a slight overestimate. But you can just report both of these as effect sizes for your full model. The second table, the ANOVA table, is a test of significance of whether this R square is equal to 0 or not. So here we see it's an F test, and the statistical significance in this case is 0.07. So this is not statistically significant. And the degrees of freedom, there are two sets of degrees of freedom you need for an F test. There are these two, the regression and residual. So this would be F with degrees of freedom 2 and 247. And again, this is testing whether the R square is 0 or whether it is not 0. And then finally, at the bottom, you have the coefficients table. And this is where we can look at our individual variables separately. So we can ignore this first row. Don't worry about this constant. That's not that important for us in this analysis. And it won't be for any of your analyses, is my guess. These last two rows are what we're interested in, where we see age and education. So this first column, unstandardized coefficients, it's a little offset there for some reason. But anyway, this is the effect of age on trust in algorithms controlling for education. So what we say here is that for every 1 year older a person is, we would expect their trust in algorithms decreases by 0.247. And then this standardized table. This is an effect size, so this just takes the coefficients and puts them on a standardized scale so they can be more comparable to one another. This is a little bit like Cohen's d. You can just report that as an effect size. And then finally, at the end, you have a significance test for each of your variables while controlling for the other. So here we have the effect of age on trust. Controlling for education is statistically significant. However, the effect of education on trust controlling for age is not statistically significant. And again, this is all here in the slides. Here we have a couple of benchmarks for R squared. A small R squared would be around 0.02, medium 0.13, large 0.26. And again, our regression output, our coefficients table. And then here are just a few more examples of tests of association that may be of interest. The chi-square test is for when you have categorical variables with no ordering. So for example, let's say you wanted to test whether men and women have different favorite brands of coffee. So let's say you let men and women each try Starbucks, Peet's, and Folgers, and you wanted to see if they tended to have different favorites among the three. Neither gender nor favorite brand of coffee has any ordering in it as a variable. So this could be tested whether there was a difference between the two groups with a chi-square test of association for categorical variables. Moderation analysis tests whether the association between one independent variable and the dependent variable changes as a function of a different independent variable. So for example, does the relationship between age and trust in statistical algorithms, which we said was significant, vary between men and women? So maybe for men, trust decreases a lot as they get older, but for women, trust does not decrease very much as they get older. There's mediation analysis, which is whether the relationship between the independent variable and the dependent variable is caused by a different independent variable. So an example might be the relationship between age and trust in statistical algorithms might be caused by increased exposure to technology. So it may be that younger people just tend to have more exposure to technology, and that's why they trust statistical algorithms a little bit more than older people. But in cases where older people also have more exposure to technology, they may also trust statistical algorithms more. So this may be a mediating variable that causes this apparent correlation. And then finally, there's logistic regression, which is just a version of multiple regression where the categorical variable, where the dependent variable is categorical. The math, it just works out a little bit differently.